So we are still on the problem solving for flywheel design. So this would be our fifth example. So now from the question, during forward stroke of the piston of a double acting steam engine, the turning moment has the maximum value of 2000 Newton meter when the crank makes an angle of 80 degree. Now with the inner dead center. Now during the backward stroke, the maximum turning moment is 1500 Newton meter when the crank makes an angle of 80 degree with the outer dead center. Now the turning moment diagram for the engine may be assumed for simplicity to be represented by two triangles. Now if the crank makes 100 revolutions per minute and the radius of gyrations of the flywheel is 1.75 meter, find the coefficient of fluctuation of energy, that would be our beta W, and the mass of the flywheel to keep the speed within plus minus 0.75% of the mean speed. So based on this, we can say the coefficient fluctuation of speed, that means the phi, will be 1.5%. Based on plus minus 0.75%, you have your phi, or the coefficient fluctuation of speed, is equals to 1.5%. So these are the two triangles which is stated in the question, which when you refer to this T theta diagram, the crank effort diagram, this would be a forward stroke and this would be the backward stroke. So the forward stroke is a triangle, and as well as for the backward stroke. So you have two triangles, one that is larger and the second one which is smaller. Now the larger triangle is based on a turning moment of 2000 Newton meter given in the question, and the second triangle is based on the turning moment of 1500 Newton meter, which is at the position at 80 degrees and 80 degrees. So when you look at both the triangles, actually the base of both the triangle is equivalent to pi radians or 180 degree. So when you take a look at this triangle, it's based on 180 degree, and this as well 180 degree. So the height for this is 2000 and for this is 1500 Newton meter. And from the diagram, we can see there are two shaded portions. Now these two shaded portion is the area that is above the mean resisting top line. So when you compare both, okay, so this would be the largest, okay, this would be the largest, and this area here, which is above the mean top line and which is the largest, will be equivalent to your will be equivalent to your greatest fluctuation of energy. Will be equivalent to the greatest fluctuation of energy. So that is why I denoted here with delta E, or you can write it as beta W. Okay. So these are the given data from the question. The speed with 100 revolutions per minute. This is the radius of gyration, so lowercase letter k, which is 1.75 meter. This is the coefficient fluctuation of speed, 0.015. Okay, and then the mass is unknown because the question asks us to find two things. One is the coefficient fluctuation of energy. The second thing is the mass of the flywheel. So based on energy balance, okay, so before we work out at the energy balance, first thing is let us find out the total area of these two triangles. Okay, we know that the area of your T theta diagram or the crank effort diagram, the area is actually equivalent to energy. So This area here, the larger and the smaller one, okay, would be equals to the total energy developed by the engine. Total energy developed by the engine, which I have written here, which is also equivalent to the work done. So the area of the first triangle is half times height, 2000, multiplied by the base, which is pi. Then plus the area of the smaller triangle, the half, multiplied by 1005, which is the height, and times the base. So this will give you the total area of both triangle, which is also equivalent to energy developed by the engine, 1750 pi Newton meter. So based on energy balance, we know that from the theory of this particular section, we know that the total energy required by the engine in real life must be equal to the total energy developed by the engine. How much required by engine must be equal to how much the engine produce. Okay, so the total energy required by the engine is actually equivalent to the area under the mean torque line. So initially or at first, we don't know this value here. So what we do is we just draw a horizontal line across, assuming that the mean resisting torque line is constant. It's constant, so it's a horizontal line across both the triangle. And then if we consider or if we find the area below the T-mean line, that would give us the energy required by the engine. That is what I have stated here, which is also equivalent to the area under the T-mean line. Then it must be equate to the total energy developed by the engine, which we have found earlier. And that is actually equal to the total area of both the triangles. So what you need to do is find out the total area of the rectangle, equate to the area of both the triangles. Rectangle area equate to the area of both triangles. Okay, so that is what I have written. So the area below the mean torque line, T times 2 pi. So that is the height multiplied by the base here, 2 pi. Okay, then equate to the area of the triangle of OAG plus the area of the triangle GLS. Okay, so which is 1750. So if I want to find the T mean, I will take this 1750 here, which is this, divided by 2 pi. Okay, so you'll be able to find out the T mean, which is 875 Newton meter here. Now, after that, the mean speed. They have given us 100 revolutions per minute, and it is not stated in the question whether it's the max or the mean or the average. So usually we will consider this as the average speed or the mean speed. So it's 2 pi n over 60. The n will be 100. So convert to radians per second. So 10.47 radians per second. So by similar triangles, based on the geometry of the triangles, we know that, let's say, for example, when we refer to these triangles, okay, we can say, okay, this length here, AE, divided by this length, CD, would be equal to the length of AB divided by the length of OG. This we call similar triangles, okay, based on the chapter on geometry on your mathematics, okay. So you will take CD divided by AE, okay, or you can take AE divided by CD. It's up to you. So if you take CD over AE, CD, which is the horizontal length, so you must equate to the larger triangle, that is OG also as well. So OG over the vertical length AB. So based on this, we will be able to find out what is the base here. Because why do we need to find out the base? Because we know that among, when we compare between these two triangles, which is above the mean torque line, which is shaded here, if I want to find the area, I will have to know the base. I will have to know the base. But since beta W, or the greatest fluctuation of energy, or delta E here, is equals to the greatest fluctuation of energy, so what we need to do is to find only this area, No need to find this area because it's understood the beta W or the greatest fluctuation of energy will be based on this larger section here, which is above the mean top line. So to find this area, you have to know the base and as well as the height. So the height can be found easily because we know that this is 2000. So, and we also know that P mean is 875. So when you take 2000 minus 875, you will get this length. So this length here can be found by what I have shown you here, okay, by geometry. So you will be able to find the CD length is actually equivalent to 1.77 radians. So from that, we will be able to find out the greatest fluctuation of energy here. So that is beta W or delta E. So the area will be half times height times base. So the height will be 1125 and the base, which we have found, 1.77. So that will give you the greatest fluctuation of energy. So and we know that beta W equals to I phi mean. Okay, this is average speed power 2. So beta W we have found that is 995.63 and then divided by this. Okay, based on this formula. So changing the subject to I. So we can find out the moment of inertia or the second moment of mass to be 605.5 kg meter square. Then after that, from there, I can find out the mass. Because we know that mass or moment of inertia is k squared. K is given 1.75. So the mass will be 197.71 kg. Okay, thanks a lot. Thank you for this section. Okay, that's for this section. So we'll continue with the next section afterward. See you. Thank you. Oh, this will be the 6th example on flywheel design. So the turning moment curve for an engine is represented by an equation of T equals to 20,000 plus 9,500 sine 2 theta minus 5,700 and cos 2 theta Newton meter, where theta is the angle moved by the crank from the inner dead center. Now, if the resisting torque, that means the mean torque, is constant, that means a horizontal line, find first the power developed by the engine, second, the moment of inertia of the flywheel, and thirdly is the angular acceleration of the flywheel when the crank has turned through a 45 degree from the inner dead center. So this would be the crank effort diagram. This is a sketch, that initial sketch, which you have a curve of H, B, C, D, E, and F. Okay, you have a curve of H, B, C, D, E, and F. This is just a sketch of a curve which is following the path of 20,000 plus 9,500 sine 2 theta minus 5,700 cos 2 theta. So the greatest section that is above the mean top line, this is your mean top line. This is an initial, okay, line which we draw, okay, an assumption. We assume that this horizontal line here go across this curve of HCDEF, which follow this equation. So this is your mean top line. So we know that area below mean top line is the energy required by the engine, and the area below the HBCDEFG to O is the area which is developed by the engine. So based on energy balance, total energy required by the engine, we have to equate the total energy required by the engine to the total energy developed by the engine. Now, so total energy required by the engine is shown as the area under the mean resisting top line. So this would be the mean resisting top line, which is horizontal, stated in the question. Resisting is constant. So this area here represents the total energy required by the engine, which is the height T mean multiplied by the base of pi or 2 pi, up to you. So here we use 2 pi. So that means this should be 360 degree, or you can take T mean times pi. Okay, so and then equate to the area under the curve. Area under the curve of O, this is the area OH, C, D, E, F, G, this area here. Okay, so when you equate both, then you will be able to find out the T mean by dividing this total area under the curve by a 2 pi. So before that, when you look at this is the area under the curve. So you have to use integration application in order to find area under the curve. So to find the work done, that means to find the total area under the curve here. Okay, so this is the work done or the energy required by the engine is the same. Work done or energy developed by the engine is the area of the under the curve. So area under the curve, you take the limits as 0 to pi or 2 pi. So you can do so with 0 to pi or 0 to 2 pi. It's up to you. So we take 0 to 2 pi. So you have this equation here. Now what we need to do is integrate this equation here with respect to its theta. Because we know that the area under the curve or the energy developed by the engine is equals to this area here under the curve, okay, which is TD theta. Okay, so the top equation which is given will be this. So you need to integrate with respect to theta, that is with respect to its variable, that means the angle theta. Taking the upper limit as 2 pi, so you have, if you have 360 degree, you will put 2 pi here. If you have 180 degree, you can put pi here. Okay, so it's up to you. So then from here, when you integrate this 20,000, you have 20,000 theta. When you integrate sine 2 theta, you have 2 cos 2 theta, negative 2 cos 2 theta. Okay, so you have negative 2 cos, cos 2 theta over 2, integration, not differentiation, yeah. Integrating sine 2 theta, I repeat, you get negative cos 2 theta over 2. Okay, integrating cos 2 theta, you will get positive sine 2 theta over 2 times negative, so that is why it's negative. So this is after integration. Then you put your upper limits and your lower limits. After substituting your upper and lower limits into this equation, you will be able to find the energy, total energy developed by the engine. That means here, this statement here. The total energy developed by the engine or the work done would be equals to 40,000 pi Newton meter. Now, you have to know integration here. So, then to find the T mean, okay, you will have work done divided by 6 pi. If this goes under 6 pi or 2 pi, what we have considered is 2 pi. This is my mistake, 2 pi. So you take T mean multiplied by 2 pi. If it is 360 degree. If it is 180 degree, you can take pi, okay? Okay, you can take pi here. So T mean times pi. So here you will have to change to pi as well. So since we have taken as 2 pi, so this one should be 2 pi. So you got a T mean is roughly around 20,000 Newton meter. So it depends on whether you take pi or 2 pi. It's the same. Okay, it's the same. Okay. So then your mean speed will be 2 pi n over 60, where the speed is 180 revolutions per minute given in the question here. So that would be mean speed in radians per second. Now, before that, okay, before we can find out, okay, the moment of inertia or the angular acceleration, but then if you want to find power, you can straight away take this T mean times omega, you will get power. You get to find the power developed, okay, T omega, or you can use 2 pi n over 60 times T, or you can take T times omega. So that will give you a power of 377 kilowatts. Okay, so to find the moment of inertia and the angular acceleration, the first thing is we have to find the greatest fluctuation of energy. That is beta W or delta E here. That is the greatest fluctuation of energy, which is also equivalent to the area which is above the mean top line. So that is this area here, that is BCD. So we don't have to find each section here. We just look at the largest area above the mean top line. So before we can find out this area by applying integration, we need to know these two limits here. Okay, these two limits here. That means starting from here, you start to add up every elementary strip until this point D. So therefore, we need to know theta A and theta D, or you can name this as theta 1 and theta 2. Now to find theta 1 and theta 2, or theta A and theta D, so at this point here, by mathematics, okay, at this point here, we say the straight line will be equals to the equation of the curve at this point, and at this point here, the straight line that is T mean will be equals to the curve equation. So you can equate T mean with the equation. So T equation of this equate to T mean, that is this 2 point here. Okay, because at this 2 point here, you can see at this intersection point here and this, the T mean line is equals to this curve here at this point and this point. So that is why we equate both of this. And we know that T mean is 20,000. And the T is given by this equation here. So when you look at this, the 20,000, both these 20,000 can be cancelled off. So what is left behind is this 9,500 sine 2 theta and this 5,700 cos 2 theta. So if you take sine over cos, you will get tangent. Okay, you will get tangent when you take sine over cos. Cos over sine is cotangent. Sine over cos is tangent 2 theta. And then 9,500, if you take 5,700 divided by 9,005, you get 0.6. You need to cancel off this 20,000 and then equate these two, because when you bring this over, become positive. When you equate both of them by getting sine over cos, then you will have 5,007 over 9,005, which is 0.6. Then if you take tangent inverse of 0.6 and divided by 2, you will get 15.48 degree. That means that is the theta A. That is the limit here. Okay. And then if you take plus 90, so let's say this is 90, you plus with this equation, you will get your theta D is the second limit. So once you have found both the upper and the lower limits, now you can go ahead by finding this area by taking at this section here and this section here, this area, you need to take the T, this is the equation T, which is above the mean top, this is the mean top, this is the equation. You can take the equation minus T mean, okay, with the upper and lower limits that which we have found. And then to find this area under the curve, you need to integrate this thing here, which is T minus T mean, with respect to its variable, that is theta. So based on this, again, the 20,000 will be cancelled out. Okay, then you integrate these two terms here. Once you integrate this, you get negative cos 2 theta over 2. And when you integrate this, you get sine 2 theta over 2. So putting in the limits, working out the equation, you will get 11078 Newton meter, which is the greatest fluctuation of energy, that is this area. So once you have found out the greatest fluctuation of energy, then you go to the second part of finding out the moment of inertia. That means this I here. The phi is given, the mean speed is given, the greatest fluctuation of energy is found. So you can find your I, that is the moment of inertia or the second moment of mass, as 3120.56 kg meter squared. That's the moment of inertia. Then the next thing is they ask us to find the angular acceleration. So according to Newton's second law, you must find T net and equate to I alpha in order to find out the alpha, that is the angular acceleration. T net means T excess. So you take your equation, T minus T mean the same thing as what you have got here, these two. That is 9,500 sine 2 theta minus 5,700 cos 2 theta at 45 degree. So what you need to do is substitute 45 here, 45 here. 2 times 45, you got 90. 2 times 45, you got 90. At 45, which is given in the question. So you got your T net or T excess is 9,500 Newton meter. That would be your T net. So by applying Newton's second law, T net is equal to I alpha. So you will be able to find out the angular acceleration of 3.04 radians per second squared. Okay, that's for example 6. Thanks. We'll continue with the next part later on. Thank you very much. If you have problems, you can refer to me, okay, later on. Now, let us refer to the last example here. The equation of turning moment curve of a 3-crank engine is 5,000 plus 1,005 sine 3 theta. Now, where theta is a crank angle in radians, and the moment of inertia of the flywheel is given as 1,000 kg meter square, and the mean speed is 300 revolutions per minute. Now, calculate the power of the engine, 1. And part 2 is the maximum fluctuation of speed of the flywheel in percentage when the resisting torque is constant. And the second one is when the resisting torque is equals to an equation of 5,000 plus 600 sine theta Newton meter. So you have 2 equations. That means you have 2 problems, 2 parts to solve. Okay, so the first part, we go for the first part when the mean resisting torque is constant. Okay, and this curve here, let's say we assume that this will be 5,000 plus 1,500 sine 3 theta, this curve here. Okay, with the constant mean resisting torque line. And then the second case is when, okay, you have something like this. That means your mean resisting torque line, instead of being horizontal, now it is following or obeying the rules or the law of 5,000 plus 600 sine theta, the curve equation. So 2 cases. So based on the first case, okay, so remember this is the energy developed by the engine. So we are finding out the area under the curve first, taking the upper limit as 2 pi and 0. Based on the first equation, first part, when the mean resisting torque line is constant, that means horizontal. So this would be the energy developed by the engine. So when you integrate this equation, you will get negative cos 3 theta over 3. Now with the upper and the lower limits of 2 pi, you can assume pi, okay, or 2 pi. It doesn't matter because later on it will cancel out, okay, 2 pi and 0. So by substituting 2 pi and 0 into the equation, manipulating and solve the equation, you'll get your energy developed by the engine or the work done is 10,000 pi Newton meter. First case. Then we know that to find the T mean, the mean resisting torque, we have this energy developed by the engine equate to energy required by the engine, which is T mean times 2 pi. So when you bring 2 pi over by taking energy developed by the engine divided by the 2 pi, you will get your mean resisting torque as 5,000 Newton meter. As I have said, when you consider this limit as pi and 0 or 2 pi and 0, you will still get the same answer of 5,000 Newton meter when you solve the whole equation. So the mean speed will be equals to 2 pi n over 60, where they have given us the mean speed is 300 revolutions per minute, converting it to radians per second. So you times with 2 pi divided by 60. So to find power, you can take T mean times omega mean. So you get a power of 157.1 kilowatt for the first case. Okay, then for the second case, or for the first case, you have here to find the limits of the curve, which is above the mean resisting torque. It's not the second part yet, it's still on the first part. Okay, by equating the T of the curve. to find out the limits. Okay, so these are the limits. So remember, you have to divide this by 3. Yeah. So that is why this is 60. This should be 3 theta, not theta. Yeah? 3 theta. So that is why you have a 60 degree. So substitute into the equation once you have integrated. So you will get your greatest fluctuation of energy is 1000 Newton meter. This is your beta W. Okay, so this is beta W. So to find out your phi, that means the coefficient fluctuation of speed, the I you have already known, the mean speed you have already known, the greatest fluctuation of energy you have known. So you can find out the coefficient fluctuation of speed, 0.1%. This is still the first part. So on the second part is this whole thing, this whole part here is the same. Only the second part of the second section is different, which you equate both the equation here. Once this mean resisting top line is no longer a constant. This is no longer a constant. Constant means because here you have 5,000. This one, it is fluctuating at the same time. So you have to solve this equation here in order to get sine squared theta equals to 0.65. So when you take square root, you will get these two angles here, which are the limits. Okay, so you have 126.27 as the upper and 53.73 degree as the lower limits. So that is still t minus t means, so you have both the equation. Okay, you have both the equation. That means this minus this. So you get something like this. Okay, then you integrate with respect to theta. After that, you substitute your limits. You can find out your beta W. It shouldn't be negative. You can consider that as positive. It doesn't matter. Okay, it only shows that it's going above or below. So after that, you can find out your coefficient fluctuation of speed, which will give you a 0.17%. That's the second section based on fluctuating mean resisting top line. This is based on the constant mean resisting top line. So the last problem is solved. So if you have any problem, you can always refer back to me. Okay, so that's the end of this section or this chapter. Okay, and thank you very much. If there's any questions or anything you want to know, you can always refer back to me. Thanks a lot, everyone.